Okay, this is section 6-3, and the title is Proving that a Quadrilateral is a Parallelogram. I ran out of room. Proving that a Quadrilateral is a Parallelogram. Okay, this section is going to be really similar to 6-2. It's actually the exact same theorems, so we don't need to add anything to our flip chart because it's the same theorems you had yesterday. It's just backwards. Yesterday you were told something was a parallelogram and you applied the theorems to the problem situation. In this case, you don't know that it's a parallelogram. They may give you some other information, but you're trying to prove that it is a parallelogram. There will be some proofs in this section. However, the book is kind of nice to you. It does give you a lot of application problems. So most of your homework will look just like yesterday's. The only difference is the question will be worded a little bit different, but you'll basically be asking to do the same thing, solving for x's and y's and stuff like that. But because there will be a couple of proofs, let me give you one example of a proof. Okay. We had the theorem that said, theorem 6-5, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So, this is theorem 6-5. If both pairs of opposite sides of a quadrilateral are congruent, then it is a parallelogram. That's the theorem. That's what we're trying to prove. So, to set up this proof, we need a picture. Okay, picture is going to be X, Y, W, Z, top right hand tool. Okay, and what are we given in this statement? In this statement, we're told that opposite sides are congruent. So that means XY is equal to WZ, and WX is equal or congruent to YZ. And that's what we're told in our given statement. And we're asked to prove, we're trying to prove that it's a parallelogram. That X, W, Z, Y is a parallelogram. So let's get started with our proof. We're going to start with the given. Okay, we know that opposite sides are congruent. So we know that that one is congruent to that one, and this one is congruent to that one. Let me get some highlighters out. Alright. Now, here's the trick on this problem. To prove this theorem, you are going to create a diagonal. Now, we spent a lot of time on triangles last semester. The trick for anything else this year is if you're not sure what to do, break it up into triangles, because you know everything about triangles. So we're going to break it up into two triangles. Now, I noticed that I have a property here that we used a lot when we did triangle congruence. XZ is congruent to XZ. Hopefully you know the reflexive property by now. We used that one a whole bunch. Okay, anytime they share a side, it's congruent to itself. So that makes that congruent. What do I notice about the two triangles? Now, I wasn't asked to prove triangles congruent, but I'm just kind of going with what I see right now. I see congruent triangles, so I'm going to prove them congruent. WXZ is congruent to triangle ZXY. And I know that they're congruent because of side, side, side. Now, remember, the whole purpose of proving triangles congruent is so that their parts are congruent. Now, think about the definition of a parallelogram. The definition of a parallelogram says opposite sides are parallel. So that's, in a sense, what I'm trying to prove. I'm trying to prove parallel lines. Now, we had a whole chapter on parallel lines, and we talked about certain special angles. I noticed some special angles in this picture. I noticed that this angle and that angle are alternate interior angles. If they are congruent, then my lines are parallel. And they are congruent because I just proved the triangle's congruent. So, angle WXZ is equal to angle XZY, because if the triangles are congruent, then all of their parts are congruent because of CPCTC. So now that I know that one's congruent to this one, then that means this line is parallel to that one. So XW is parallel to YZ. And that's because those angles are alternate interior angles. Now, I also have another set of alternate interior angles here. I have that one and that one. Those angles are also alternate interior angles, and they are also congruent by CPCTC. They're congruent because the triangles are congruent, and because they're congruent, then that makes this line parallel to that line, because they're alternate interior angles. Now that I've proven both opposite lines parallel, then I can say that it's a parallelogram by the definition of parallelogram. Okay? So, that's one example of a proof. They won't all be that long, they won't all be like this, and you won't have very many. Most of your problems, like I said, will be similar to what you had yesterday, so let me give you one example of that. And remember, everything's going to be a parallelogram, so. Thing. What did we just learn about parallelograms? We learned that the opposite sides are congruent, right? So if opposite sides are congruent, then we just set them equal. Subtract the C. C minus 3 equals 1. Add 3. C equals 4. Divide by 2. C equals 2. Now, what do I know about these angles? Remember, we did this the other day. If I have parallel lines and a transversal, that makes this and this same side interior angles. We have same side interior angles, which means they're supplementary. So A plus 40 plus A equals 180. Supplementary means 180. Combine your like terms. Subtract 40. And divide by 2. And you get 70.